Okay, perhaps we can get started. I have two brief announcements. One is that there will be a group photograph taken after the morning session. So no matter how hungry you are on your way to lunch, you should stop at Fold Hall where we have coffee and tea and assemble there for a group photograph before going off to get your lunch. The second is I've been asked to say that for a variety of reasons, we have somewhat heightened concerns about communicable illnesses and flu. This is mostly a general reaction to heightened concern everywhere. Of course, there's only a limited amount that we can do to prevent this, but we do strongly urge you, if you feel any illnesses that might be flu or something communicable, first of all, to not come to the lectures. Second, to wash your hands and avoid and do everything possible to try not to communicate it. And third, to contact Susan, who can arrange for a doctor's examination very quickly. The other thing that we'll do is to provide hand sanitizers outside on the table out there, and we encourage you, of course, to wash your hands and to use the sanitizers. Okay, on to the lecture. This morning's lecture is on geometric methods for orbit integration. And let me first remind you that orbit integration is one of the really fundamental components of a very wide variety of problems in astrophysics. As an example, this is one example, of course, is spacecraft trajectories. This is the 5-year trajectory of the Cassini-Huygens spacecraft around Saturn. The more or less circular orbits are Saturn's satellites, and the multicolored elliptical orbits are this complicated trajectory which was designed ahead of time to enable Cassini to visit as many of the satellites as possible. Second, by far the oldest concern about orbit integration is planetary orbits. This is an example showing as solid lines here the orbits of the current orbits of the innermost planets. So this is Venus, Earth, Mars. The dots are, this is Mercury, Venus, Earth, and Mars is only just visible because the reproduction isn't very good. The dots are the same planetary orbits over 50,000 year period, 4.5 billion years in the future. The fact that they're still there tells you basically that the solar system is stable. And of course, as Volker Springel told you yesterday, in cosmological simulations are basically a problem of integrating a very large number of orbits of bodies representing dark matter particles over a Hubble time. There are other contexts. Understanding galactic structure requires understanding the rather complicated morphology that orbits can take in the overall galactic potential. And of course, one of the more interesting subjects in the last few years has been the study of orbits of stars very close to the black hole in the galactic center. Orbits are also important in other contexts. Perhaps the most obvious is the Large Hadron Collider, where the design of the collider requires that they can calculate very accurately the orbits of large numbers of particles around this vast storage ring. Obviously, there are huge differences in the different problems that I've mentioned. Probably the most basic one is the number of orbits that you have to calculate. For something like Cassini, you only need to do maybe a few hundred orbits. In galactic structure, you need typically 100 to 1,000 orbits. In cosmological simulations, obviously the answer is basically the same because you're trying to resolve what's happening in the inner parts of galaxies. In the galactic center, given the lifetimes of these stars of around 10 million years, you're talking up to 10 to the 6th orbits. In the Large Hadron Collider, for a storage time of about half a day, you need to follow a much larger number, around 10 to the 9th orbits. And for planetary systems, you need to follow 10 to the 10th orbits. If you're trying to follow an orbit for 100 orbital periods or even 1,000, pretty much any integrator will do. You can just pick one out of numerical recipes or any other source that you like, and it'll work fine if you use enough time steps and the orbit isn't too pathological. On the other hand, once you're trying to get to 10 to the 9th or 10 to the 10th orbits, you have very worrisome problems in that any small buildup of numerical error can easily completely change the nature of the orbit and can completely invalidate your conclusions. And so what I'd like to do is try to describe what the problems are that arise with these very long orbit integrations and how they can be solved. So during this lecture, what I'm going to try to do is alternate back and forth between the projector and the blackboard. I hope the blackboards will be visible, but if they're not, you may want to consider moving forward a little bit in your seat. Okay, so just any orbit integration problem is basically a problem of solving a set of ordinary differential equations as a function of time. So you can always write that as some vector is some function of the time and the vector. There are many simple examples of this. So for example, the simplest one is a one-dimensional harmonic oscillator. X double dot is minus omega squared x. In this case, the vector y is just position and velocity, where v is x dot. And the equation of motion is just that dy dt is a matrix 0, 1, minus omega squared 0 times y. The first row of the matrix just says x dot is v. The second one says that v dot is minus omega squared x. That one, of course, you can do analytically. Another one you can do analytically that's the basis for much of what I'll talk about is an orbit around a point mass. In this case, the acceleration is equal to a force, and the force is minus gm over r squared times the unit radius vector. Again, the velocity is r dot. The parameter y is r and v, and dy dt is just v, and the force is a function of position. More generally, most of the systems that I described up there can be thought of as being described by a Hamiltonian. H, which is a function of some generalized coordinate and generalized momentum. The equations of motion are Hamilton's equations, which say that the rate of change of the position is plus partial of the Hamiltonian with respect to momentum, and dp dt is minus partial of the Hamiltonian with respect to position. And then, of course, the equation of motion is just that dy dt, where y is q and p, is just dh dp and minus dh dq. So most of the systems that you deal with in astrophysics are of this kind. So that's the exact set of differential equations that you're trying to deal with. What we're trying to do is find a numerical approximation to these equations, which again I'll write as dy dt is some function of the time and the position. You're going to try to pick some finite time step to go from time n to time n plus 1 with some time step h. And in general, of course, the way you're going to do this is to find some formula that says that the vector you're interested in at n plus 1 is equal to its value at n plus some function that depends on yn in the time step. And it could also in principle depend on the time. This looks completely general, but of course it isn't quite completely general. By writing it in this form, I've restricted myself to an explicit integration scheme. That is a scheme in which yn plus 1 can be written down as an explicit formula in the quantities that you know. The more general form would be implicit, in which there's some equation w of y n plus 1 yn h and tn that you have to solve numerically in order to get the next time step. This is also a restriction to one-step methods. Again, a more general form would be a multi-step method, which would say that yn plus 1 is yn plus some function of yn, n minus 1, and so forth, and the time step and the time. There's nothing wrong with implicit methods. There's nothing wrong with multi-step methods. I'm just not going to talk about them here. The other thing that you need to know about a method is the order. And the order is very simple to define. It says that if the true solution is y of t, and if y naught is equal to the true solution at 0, then the difference between y1 and y of h, that is the difference between the exact solution after one time step and the solution from your numerical method, is going to be proportional to some constant a times h to the n plus 1. And then n is the order. Okay, now, if you read any numerical analysis book, what they'll tell you about integrating ordinary differential equations is that you should try to maximize the order and minimize the coefficient in front of it, and that you design a numerical algorithm to try to accomplish those two goals, to make the order as high as possible and the coefficient as low as possible. And what I want to try to persuade you of is that if you're trying to integrate orbits for a very long time, that's not always the right thing to do. Okay, so let me go back to the slides, please. Okay, so to try to persuade you of this, I'm going to describe a very simple system. A particle, a test particle, orbiting the force field of a point mass. I'll set the mass of the attracting body to unity. I'll set g to unity. And that means that the equations of motion are simply that the rate of change of position is velocity. Rate of change of velocity is the force, which is a minus attractive 1 over r squared force. I'm going to illustrate how you integrate this with three different methods. The first of them is Euler's method, which is the simplest, dumbest integration scheme that everybody thinks of the first time they try to integrate a differential equation. You just advance the position from step n to n plus 1 by the time step times the velocity. Then you advance the velocity from step n to n plus 1 using the time step times the force. The second is just as simple. It's a modified Euler's. The only difference from ordinary Euler's is that when you advance the position, instead of using the old, when you advance the velocity, instead of using the force at the old position, you use the force at the new position. The third example is Leapfrog, in which you first take a step like this from Euler's method, except you only advance for half a time step. Then you advance the velocity using this position, and then you advance the position again by half a step. If you work out the algebra, the first two methods are first order. That is, the error after one step is of order the square of the time step. Leapfrog is second order. And I'm also going to describe the results from a fourth method, the standard Runge-Kutta method that you find in all the numerical analysis textbooks, which is a fourth order method. Now, if you're going to do a comparison between these, you have to do it on a level playing field. And the best way to establish a level playing field is not to give them equal time steps, because a time step of Runge-Kutta is a lot more complicated, but to imagine, as for example is the case in a cosmological simulation, that the really time-consuming step is the force evaluation. So we're going to pick the step sizes so that all of them have equal numbers of force evaluations per unit time. Okay, if you do that, these are the results for an orbit with a modest eccentricity, a couple of hundred force evaluations per orbit, and I'm measuring the accuracy by the fractional energy error in the numerical orbit, which of course ought to be 0. The first thing you can see is that the first of the methods, standard Euler's method, is absolutely terrible. You should never use it. After only about 10 orbital periods, the energy error is of order unity. This is a totally useless method. Second thing you can see is that Leapfrog in green is doing better than modified Euler in blue. That's certainly what you'd expect because it's a second order method instead of a first order method. Next thing you can see is that the Runge-Kutta method in red is doing better than any of the other methods in here. Again, that's what you would expect because it's a fourth order method and it ought to do better. However, the striking feature is that the energy error in Runge-Kutta is growing with time as some power of the time, whereas the maximum energy error in the other two methods is exactly flat. These curious oscillations, of course, are because I'm taking the absolute value on a logarithmic scale and it's oscillating between positive and negative. But what you can see is that even after 100 orbits, Runge-Kutta, although it's a fourth order method, is doing orders of magnitude worse than Leapfrog. And as you can imagine, if you tried to follow this for 10 to the 9th orbits, Runge-Kutta would be totally useless compared to these much simpler methods. And the question is, what's going on? Why are these two methods doing so well, likely to do so well over very long times compared to Runge-Kutta? And the basic answer in this case is Liouville's theorem, which most of you should have seen in a course on statistical mechanics. Liouville's theorem simply says that if you have a phase space and you have a Hamiltonian, then the flow in phase space of the cloud of points generated by this Hamiltonian conserves phase space volume. That is that the density of points around a given point in phase space is going to remain constant. So what does this have to do with integration methods? Well, let me go back to the blackboard. So mathematically, what Liouville's theorem says is that if I have some flow, so first of all, I'll define y to to be the vector in phase space consisting of the coordinate and the momentum. The next thing I'll do is to define a flow which says that y is a function of time and y0 is basically the phase space position of something at time t that was at y0 at time 0. So basically y of 0, y0 is equal to y0. And then Liouville's theorem simply says that the Jacobian of y relative to y0 is 1. So you take this function, calculate the partial derivatives of the components of y with respect to y0, calculate the determinant and its unity. That's basically saying that the phase space volume is conserved by the flow. Okay, so now let's look at Euler's method. Euler's method, once again, I'll just do this in one dimension to keep the algebra simple. In one dimension, Euler's method says xn plus 1 is xn plus time step times vn, and it says that vn plus 1 is vn plus h times the force at xn. So I can evaluate the Jacobian of xn plus 1, vn plus 1 over xn and vn. Well, if you look at the determinant, xn plus 1 depends on xn as 1, depends on vn as h. Vn plus 1 depends on xn as h, f prime of xn, and it depends on vn as 1. And so the Jacobian is 1 minus h squared f prime of xn, which is not unity. So Euler's method doesn't satisfy Liouville's theorem. Okay, so the next thing to try is the modified Euler method. With modified Euler, just as with regular Euler, xn plus 1 is xn plus h times vn, and vn plus 1 is vn plus h times f of xn plus 1. The Jacobian, xn plus 1, vn plus 1 relative to xn is, once again, partial of xn plus 1 with respect to xn is 1. Partial of xn plus 1 with respect to vn is h. Partial of vn plus 1 with respect to xn is a little more complicated. It's h times f prime at xn plus 1 times the partial of xn plus 1 with respect to xn, which is 1. Partial of vn plus 1 with respect to vn is then, there's a 1 here, and then there's a term from this. There's plus hf prime of xn plus 1 times the partial of xn plus 1 with respect to vn, which is another h. And so that makes that an h squared. And if you stare at that for a moment and you work out the Jacobian, it's 1. So regular Euler doesn't satisfy Liouville's theorem. Modified Euler does satisfy Liouville's theorem. And the basic reason why modified Euler works so well is that it satisfies this theorem, this geometrical property of the original Hamiltonian flow. And because it satisfies this property, it's sort of constrained on where it can go in phase space, and that eliminates the drift in the energy error. Okay, now what about Leapfrog? You can go through the calculation and see what happens with Leapfrog, but it gets a little messy algebraically, and there's actually a simpler way to do it. To explain what the simpler way is, let me go back to this description of modified Euler. A convenient way to think about modified Euler is to think about these two steps separately and to label them differently. This step is called a drift step. The reason it's a drift step is that if you think about it, if you look at this step alone, the velocity doesn't change, the position does change, and it's basically equivalent to the particle just drifting down a river at constant velocity without any acceleration. In this step, on the other hand, if I consider this step alone, the position doesn't change, only the velocity changes. The velocity changes impulsively. It's as if you took the particle and you gave it a kick, and so this is called the kick step. Okay, now let me erase this so that I don't have to obscure that. Once you introduce this notation, then this particular form of modified Euler is called drift kick modified Euler. Because you first drift and then kick. But there's nothing special about doing things in that order. You could equally well have kick drift modified Euler. In that case, you'd first say Vn plus 1 is Vn plus h f of xn. Xn plus 1 is xn plus h v n plus 1. Either of these two is equally legitimate. You can go through the same algebraic calculation and show that either drift kick or kick drift both satisfy Liouville's theorem. Once you've recognized that, then it's easy to see what's going on with modified Euler. It's easy to see what's going on with Leapfrog because Leapfrog is just half step of drift kick. A full step of kick drift. And another half step of drift kick. So we've argued that each of these three components of Leapfrog satisfies Liouville's theorem. So the phase space density is conserved, or phase space volume is conserved in this step, and this step. Therefore, it must be conserved in Leapfrog. So we've shown that Leapfrog satisfies the same geometric property as both flavors of modified Euler. It satisfies Liouville's theorem, and that's the basic reason why it behaves so well. The reason that Runge-Kutta doesn't behave so well and that regular Euler doesn't is that they don't satisfy Liouville's theorem. So this is the general philosophy of geometric integration algorithms. They're numerical integration algorithms that exactly conserve some geometric property of the original set of differential equations. What I've used for illustration is volume-conserving algorithms, which conserve the phase space volume. They're appropriate for any Hamiltonian system because any Hamiltonian system satisfies Liouville's theorem. And again, the examples include modified Euler and Leapfrog. But that's not the only geometric property that you might choose to use. You could also look at energy conservation. Any motion in a fixed potential conserves energy. Geometrically, it says that you have a whole phase space, but there's an energy surface of lower dimensionality in the phase space, and the system has to stay on that energy surface. And so if you can find an integration algorithm that keeps you on the energy surface, it's going to behave better than one that doesn't. None of the methods that I've described, modified Euler, Leapfrog, or Runge-Kutta, are energy conserving. People do use energy conserving algorithms sometimes, but they're not very elegant. What they basically do is they take a step and then they say, oh gee, the energy is not conserved. And so they sort of pump up all the velocities and change the positions to get the energy conserved again and then keep going. So those, although those are powerful in principle, they haven't actually had very much applicability. Another geometric property is time reversibility. It's very easy to tell whether an integration algorithm is time reversible. You simply integrate forward for some number of steps. You stop, you change all the velocities to minus the original value. Integrate backward in time, integrate again for another n steps, change the velocities again. And if you end up exactly where you started, it's time reversible, and if you don't, it isn't. A wide variety of systems are time reversible. So for example, the gravitational n-body problem is time reversible. And so it's reasonable to suppose that time reversible systems will integrate the gravitational n-body problem better over very long times than systems that aren't. Out of the systems we've looked at, modified Euler is not time reversible. Runge-Kutta isn't time reversible, but Leapfrog is. I've written down Leapfrog again, and if you stare at that for a few minutes, it'll eventually become clear to you that if I integrate one step forward, change v to minus v, and then integrate back, change v to minus v again, I'll end up exactly where I started. So one of the reasons Leapfrog works so well, and one of the reasons that it's so popular, is that it actually has two independent geometric properties, volume conservation and time reversibility, and that in some sense makes it an even more powerful algorithm for long integrations. The final geometric property is symplectic integration algorithms. I'm sure most of you slept through most of your last classical mechanics course, but all of the stuff they told you about Hamiltonians sometimes really is useful. Again, any system governed by a Hamiltonian satisfies Hamilton's equations of motion. And once again, if I write the flow governed by the Hamiltonian as some function y of time, then the flow from y at some initial time to some final time that's generated by the Hamiltonian is a symplectic map or a canonical map. And an integration method is symplectic if the formula that you have for advancing by one time step is also a symplectic or a canonical map. There are two basic ways of determining whether this is true or not. As you may or may not recall from your last course, canonical transformations can be generated by a generating function, but in practice, a simpler and better way to recognize it is that because anything generated by a Hamiltonian is symplectic, if you can generate your integration step using a Hamiltonian, you're guaranteed to have a symplectic integration algorithm as well. For a system with one degree of freedom, that is one position and one velocity, so a two-dimensional phase space, symplectic is the same as volume conserving. But for systems with a higher number of degrees of freedom, symplectic is more general. And so you'd like to have integration algorithms that are not just volume conserving, but actually symplectic. It turns out that modified Euler and Leapfrog are symplectic, and I'd like to try to persuade you of that next. But just before doing that, let me try to give you a kind of intuitive feeling for why geometric algorithms work better for orbit integrations. Let me imagine that I'm just following a particle on a circular orbit. So this curve is intended to represent a circle. And we'll start off with the particle, say, here. And I'm going to try to advance it by one time step. The instructions that you get when you read a standard numerical analysis book are that you should try to minimize the error after one step. So let's suppose that this is the true position after one time step. The method that you get from the numerical analysis book will try to get this point as close to that as possible. And it may be that the best place, the closest it can get, is there. So this is, say, Runge-Kutta. The geometric algorithm is so constrained, hopefully, by its geometric properties, such as time reversibility or being symplectic or being volume conserving, that it won't be able to get there. That's not allowed by the geometric constraints. So it will end up not as close to the true point, but maybe it'll end up here. So this is geometric. So this distance is bigger than this distance. So in the view of the conventional numerical analysis book, this is better. The trouble is that as you keep going more and more steps, this particle is going to spiral in and eventually just spiral into the center of your attracting mass point, which is a completely unphysical behavior since there's no dissipation in the system that we're looking at. The geometric system will continue to go more or less along this curve. This isn't quite correct. It may oscillate back and forth, but it won't have any spiraling behavior. That is, it won't have any numerical dissipation. And so over very long times, phase errors are simply so much more benign than errors in the energy that you're better off with the geometric method. Okay, so what I'd like to describe now is why Leapfrog or modified Euler is a symplectic method. And in the process, I think we can generate a considerable amount more insight into how the system works. Okay, so in general, we're trying to follow, if we're looking at one particle, one test particle, we're trying to follow motion in a Hamiltonian. And the typical Hamiltonian for a test particle of unit mass is simply a half p squared plus some potential that depends on the coordinates. And this satisfies, the motion satisfies Hamilton's equations. So again, p dot is minus dh dq, and q dot is dh dp. This Hamiltonian consists of these two terms. We can write it as HA plus HB, where HA is the kinetic energy part, a half p squared, and HB is the potential. Okay, so what I'd like to suggest now is that we look at the evolution of the system under the Hamiltonian HA alone. So we'll forget about HB. If all we're doing is following the Hamiltonian flow under HA, p dot is the h dq, but there's no dependence on q, so p dot is 0. So under HA, p dot is 0, and q dot is dh dp, which is just p. So if I integrate that over a time h, I get q prime is q plus hp, p prime equals p. And this should look familiar, apart from the difference in notation from position and velocity to coordinate and momentum. This is simply one drift step. Or maybe a little more mathematically, I'll say that y prime is some operator A of y, where A is the drift operator. Okay, I can do the same. I can do the same thing under HB. HB, you'll recall, is just phi of q. And then Hamilton's equations say that q dot is dhb by dp. That's just 0. P dot is minus dhb dq. So it's minus d phi dq. And so that says that under time step h, q prime is equal to q, p prime is equal to p minus h d phi dq. And that, of course, is one kick step. So again, more mathematically, I can define an operator which says that y prime is some nonlinear function b of y, and I'll call that the kick operator. And maybe to make the fact that this is advancing y under a time step h, I'll put a subscript h under the kick operator, and I'll put one here under the drift operator as well. So once we've defined these operators, kick drift modified Euler is just the sequence which says that y prime is a function of y. The first thing we do to y is we hit it with a kick. So that's, you operate on it with BH, then you do a drift, you operate on it with AH. If I do drift kick, modified Euler, it's just y prime is BH AH of y. And then, of course, Leapfrog is just y prime equals, there's an AH over 2 BH AH over 2 operating on y. So what have we learned from this? Well, first, this automatically tells us that all three operators are symplectic, because the kick operator and the drift operator are both derived by a Hamiltonian, so they have to be symplectic. And when you compose symplectic operators, the result has to be symplectic. So Leapfrog has to be symplectic, as does these two. The second thing you learn from this is that it's clear why Leapfrog is symmetric, because this combination of A's and B's is symmetric, time symmetric, and it's clear why modified Euler isn't. The other thing you learn is that this suggests obvious ways to generalize these integration algorithms. So for example, suppose I take these operators and I make a even more general looking operator. I'm going to say y prime is equal to A times alpha h, where alpha is some dimensionless number, B beta h, A gamma h, B delta h. I'm running out of space, but A gamma h, B beta h, A alpha h times y. So this is just a sequence of kicks and drifts. And I want to make a nice integration algorithm out of this. Well, if I'm going to make this represent an advance over a time step of h, it's pretty clear that if there was no gravitational potential, that is, then B would be unity, all you'd have is the A's, and you'd want all of these coefficients to add up to unity. So it's pretty clear that 2 alpha plus 2 gamma has to be 1. Similarly, if there's no drifts, you'd like the coefficients of the B's to add up to unity. That says 2 beta plus delta ought to equal 1. But this is 2 constraints on the 4 numbers, and so you've got some extra freedom. So you can choose the other 2 numbers to make this a higher order scheme than Leapfrog. This strategy was first recognized by Fourier and Routh, and this is sometimes called the Fourier-Routh integration algorithm. It turns out that the answer is that beta is 2 alpha is 1 over 2 minus 2 to the 1/3. This gives you a 4th order algorithm. It's symplectic. It has to be symplectic because each of these operators is symplectic. It's time reversible because the pattern is symmetric. And so, you've easily generalized Leapfrog to a 4th order integrator. You can do more. You can have longer and longer chains of these and generate 6th order, 8th order, 10th order, any order you want. In practice, the only problem with these is that they seem a little funny because it turns out that in almost every case, some of the steps are backwards. So instead of just sort of working your way across the integration algorithm, you actually have to overshoot and then come back. So that seems a little strange, but in practice, they actually work quite well. Mm-hmm.
Can you take variable time steps?
I'm coming to that. Yeah, okay. Okay, so what are the other applications of these? One of them is, this is simply a follow-on to some of the points that Volker made yesterday. You can use these techniques to generate an integrator working in co-moving coordinates. As Volker showed, you can write the Hamiltonian in co-moving coordinates as a combination of a kinetic energy term involving the scale factor and the co-moving momentum, and a potential term arising from the interactions between the particles. And you can then make exactly the same split. You think of this as your drift operator, you think of this as your kick operator, and then the kick operator advances the positions this way. Sorry, the drift operator advances the positions this way, the kick operator advances the positions this way, and you combine them as I described over on that blackboard. Whoops. And out of that you get a Leapfrog scheme in co-moving coordinates. The other major application is to long-term planetary integrations. In this case, if I look at the simplest case of a test particle in a planetary system, it will have a Hamiltonian for unit mass test particle that involves a kinetic energy term and a potential energy term. In this case, the potential energy term is the combination of the gravitational potential due to the central star or to the sun and the potential from all the other planets. The natural thing to do is to say, well, I'll integrate this with Leapfrog. I'll take HA to be the kinetic energy term, HB to be the gravitational potential, and that's a perfectly legitimate and perfectly fine integrator. But in fact, you can do much better. And the way you do better is to take the term from the central star or the sun and move it over into the first part of the Hamiltonian so that the second part of the Hamiltonian, HB, is only the planetary potential. Now, why does this work? Well, the critical thing is not, the only thing that you need for doing this kind of split is that the motion under each of the Hamiltonians individually can be integrated analytically. Well, we've seen already over here that you can integrate the motion under either of these analytically, but even after you do this split, this is just the Kepler Hamiltonian, and ever since the time of Newton, we've known how to integrate this analytically. This is a Hamiltonian that only depends on positions, and since it only depends on positions, it's an absolutely standard kick operator. Why is this an advantage? Well, basically because all of the errors that arise in any integration algorithm of this kind arise because operating with one Hamiltonian and then another and then the first one again is not the same as operating with both of them together. But because this Hamiltonian is very much smaller than this one, in fact, it's smaller by the ratio of planetary masses to the central stellar mass, the errors introduced by the split drop by many orders of magnitude when you do this. This line of argument has led to the integrator that's almost universally used now to follow planetary systems. It was first worked out by Wisdom and Holman in 1991. It's often called a mixed variable symplectic integrator, and it basically involves making a Hamiltonian split into a Kepler part and a planetary perturbations part. It's called mixed variable because the best way to integrate this is in using orbital elements or action angle variables, if you like, in which, because in orbital elements, of course, the orbital elements are fixed in a Kepler potential, so the integration is trivial. This is best integrated in standard Cartesian coordinates, and since this is a kick operator, the integration here is trivial. So basically, all of the work in the integrator is switching back and forth twice every time step between orbital elements and Cartesian coordinates. There are very efficient ways to do this because people like Gauss used to have to do this by hand, and so they thought very carefully about how to do it efficiently. And so basically, all of the work in your integrator is switching back and forth between these two sets of coordinates, and then just integrating using Leapfrog. This is a geometric integrator because it's symplectic, because it arises from a Hamiltonian. It's time reversible because Leapfrog is time reversible. The errors are smaller than ordinary Leapfrog with the split into kinetic energy and potential energy by a factor that's typically the ratio of the planet mass to the stellar mass. So it's a factor of 10 to the 4 or so in the solar system. And although I won't go into them, there are many nice techniques you can use to reduce the errors still further. So for example, one of them is that it turns out that most of the long-term error arises because you start the numerical integration with the steps you eventually want to, with the steps you want to use over the very long term. That turns out to be such a shock to the system that it creates long-term errors. But in fact, if you start off with a very small time step and gradually and slowly increase the time step up to the final value you want, and then run along with, after sort of slow acceleration, you run along at the final time step, you can show that that reduces the error by another factor of the ratio of the planet mass to the mass of the central body. You can think of this as being basically saying that you want to adiabatically change change from the real system to the numerical system. Okay, so what this kind of thing does extremely well is to integrate planetary systems that are in more or less circular orbits for very long times. The place where it doesn't do too well is when you have a chaotic planetary system with big eccentricities or close encounters with the planets. That, of course, is exactly what you get in a gravitational n-body system, like a star cluster or a galaxy, and that's one reason why this method has not been used, for example, for following the motions of stars close to the black hole in the galactic center. Nevertheless, for planetary systems, it works very well. There are a variety of public software packages that do this, in particular Mercury and Swift. They typically include several integrators that you can switch between to compare how well they're working. They allow you to handle close encounters with a variety of techniques. They allow you to put in extra test particles. They allow relativistic corrections and so forth. One of the problems in the homework exercise is to do a simple integration using Mercury. And typically, if you want to follow the solar system for 1 million years now, you can do so in about 30 minutes. So integrations for the whole life of the solar system, 5 billion years, are a pretty major undertaking of some months, but perfectly feasible. This is an example of the state of the art from a paper in Nature just a couple of months ago. In this case, because the solar system is chaotic, in order to figure out what's going to happen over a very long time, you have to do a lot of different integrations. So what was done in this calculation was to do something like a couple of thousands of integrations of the solar system. Because the system is chaotic, very small changes in the initial condition are sufficient to explore phase space. So in this case, they varied Mercury by some random number, Mercury's initial position by some random number between 0 and 1 millimeter. It gave a huge variety of different behaviors for the eccentricity of Mercury over 5 billion years, but you can see that in some small fraction of them, Mercury was chaotic enough that it went to very high eccentricity and then presumably collided with Venus or fell into the sun or had some other uncomfortable fate. Okay, well, as Mike indicated, there is one dirty little secret about symplectic and geometric integrators, which is everything I've talked about is for a fixed time step. If the time step is not fixed, you start to have rather serious problems. And the reason for that is pretty simple. You recall that if I write down a general formula for a one-step integration method, that method is symplectic if the Jacobian is 1. If I'm going to have a variable time step, the variation of the time step is going to have to depend on position, so it's going to be a function of yn, and you can pretty easily see that if this was true when h was fixed, once you allow it to depend on position, in general this Jacobian is no longer going to be unity, it's no longer going to be volume conserving, it's therefore no longer going to be symplectic. And in general, basically once you vary the time step, all of the good properties of geometric integrators are lost. So the question is, and that's okay when you're following something like a planetary system with well-behaved orbits. It's okay in something like the Large Hadron Collider, but in a lot of systems it isn't. And so it's very useful to try to figure out ways to fix the problem. And there are techniques for fixing the problem that work in some cases, but not others. Okay, so if we want to allow a variable time step, something that depends on position and velocity, it turns out that the best thing to do is to recognize that although it's very hard to make a symplectic integrator with a variable time step, it's not quite as hard to make a time reversible algorithm with a variable time step. And time reversibility gives you almost all of the good geometric properties of being symplectic. So the first thing to do is to say, well, all I'm going to try to do is make a time reversible algorithm. And here's one way to do this. The first step is to define some symmetric function of the new and the old time step. So for example, it could be h plus h prime over 2. It could be 1 over h plus 1 over h prime. Any function that's symmetric in the two arguments would do. Then I take standard leapfrog. I advance the position by half of a drift step. Then I advance the velocity by half of a kick step, in contrast to the conventional leapfrog that advances at a full kick step. Then I write down this symmetric function is equal to the time step that I would like. We've started off with some given time step, so I can solve this equation analytically with this function to get the new time step. Then I advance half a kick step with a new time step, half a kick step, half a drift step, and then half a drift step. You can see, if you stare at this for a little while, that if the time step wasn't varying, if I just kept h equal to h prime, this would be standard leapfrog. You can also see that this procedure is completely time symmetric. So this does give you a time symmetric integrator, which one would hope would maintain most of the good geometric properties of an integrator with a fixed step. This is the same system that I looked at before, except with a somewhat higher eccentricity of 0.5. The black line is just following this orbit with standard leapfrog with a fixed time step. The energy error, maximum energy error, the envelope of the energy errors is fixed, as we've come to expect. If I then take standard leapfrog and vary the time step naively, you just change the time step after every leapfrog step, the energy error looks like this. And as advertised, you've completely lost all of the good behavior of geometric integrator. On the other hand, if I use the algorithm that was described on the previous slide, not only is the energy error fixed again, but you've gained most of an order of magnitude in the energy error simply because you're using smaller time steps when the particle is close to the central star, and the smaller time steps help you follow the orbit more accurately. Okay, so that's one technique for allowing variable time step. A second possibility is to use time transformation. If you want to use a variable time step that depends in some way on phase space position, one way to do it is to introduce a new time variability, a fictitious time, that's related to the real time by the desired time step. And then if you can somehow cast your equations in terms of the fictitious time, fixed time step in the fictitious time corresponds to the time step change you want in the real time. And the way to do this is a technique which again should have been familiar to you if you weren't sleeping in your last class on Hamiltonian mechanics. If you want to, it's one of the things they tell you when you deal with Hamiltonians is that if you want to convert a time variable Hamiltonian to a fixed or an autonomous Hamiltonian, you do it by working in an extended phase space in which you add to the usual configuration space an extra coordinate, which is just the time, and add to the momentum space an extra momentum, which is minus the energy or minus the Hamiltonian. If you then write down a new Hamiltonian that involves the old Hamiltonian and the time step with a formula like this, and write down Hamilton's equations, you can show that they're exactly the same as the Hamilton's equations with the original Hamiltonian, but now written in the fictitious time. And then you can integrate this new Hamiltonian by a standard symplectic method. This method works extremely well. The only problem is that it only basically works for one particle, because if you have different particles, they ought to use different time steps, and you can't synchronize the time steps of all the different particles because the fictitious time for each particle is different. This is an example of one of the problems of geometric integration that I think is still an active area of research, and one where the right idea may be able to make a big difference sometime in the future. Sorry, there are no time transformations you can do to. No, the problem with the variable time step is that it's the time step you'd like to have individual time steps for different particles. If a particle is out at 500 astronomical units, you'd like it to have a larger time step than one that's in at a tenth of an astronomical unit. And when you're transforming the fictitious time, everything has to have the same time scale in order to calculate forces simultaneously. And so you're always stuck with, it works well for one particle, but it doesn't work well for many particles, because you're always stuck using the smallest time step for any particle for all the particles. This is a third and final possible technique. One of the things that you'd like to do is move beyond just Hamiltonian systems. So let's imagine, for example, that you have a completely general differential equation, but you know that from the physics that it's time reversible. Is there a way to generate a time reversible integration scheme, even if the system isn't Hamiltonian? And the answer is yes. You'd like to use a time step that's some function of this coordinate y, which may not be a phase-space coordinate. Again, you define some symmetric function of the two time steps. And then you pick any integrator you like. It can be Runge-Kutta, it can be Buller-Stewart, it can be anything you like. It's some sort of one-step integrator. And then the neat trick, which was originally due to Mikkola and Merritt, is that you introduce some dummy variable and set it equal to the variable that you want at step n. Then you do something that sort of looks like Leapfrog. You advance your variable for half a time step using your integrator. Then you take the other variable, and instead of adding this function, you subtract it with its value at minus half a time step. Then, just as with Leapfrog, you change the time step according to your criterion. Then advance the dummy variable half a time step, and advance this one with a minus sign here by minus half a time step. Now, why do you go through this? Well, the answer is obvious after you stare at it for a little while. If you stare at this for a while, you'll see that this scheme with the two variables is completely time reversible. And so what this has done is taken any integrator, which is otherwise, which has other desirable properties, and converted it into a time reversible integrator. Okay, that was most of what I wanted to say. The basic point that I think you should carry away from this is first, that if you have any physical system where the physics tells you that there are certain conserved quantities that restrict the possible behaviors, and you're trying to integrate that for a very long time or very accurately, then it's a good idea to try to find an integrator that incorporates the same symmetries that the original system does. The second is that, at least for Hamiltonian systems, this is one arena where Hamiltonian mechanics really allows you a lot of insights that have permitted very powerful techniques that you probably would never have been able to derive or figure out just without the sort of generality of Hamiltonian mechanics. Third point is that this is very much an active area of research, and there's a lot of opportunities for advances or new techniques that are pretty simple but can have really dramatic effects on your ability to do very high accuracy long-term calculations. I've left out a lot of subjects for cosmological simulations or simulations of star clusters. And for many situations, individual time steps are absolutely essential. There are some techniques, these limited techniques, for incorporating individual time steps in geometric integration algorithms, but there's still a lot left to be done, and I haven't tried to describe those. I've left out the general topic of regularization, of changing the coordinate system to eliminate singularities in the motion, particularly for highly eccentric orbits that are very hard to follow. I've left out non-geometric methods for n-body integrations. In many of the standard n-body codes, they use techniques like Hermite integrations or multi-step, multi-value methods that are not geometric, but in practical purposes still work very well because the systems are so chaotic and have so many close encounters that the most important thing is to follow those as accurately as possible. I've left out the subject of round-off error, which is a really interesting one in itself, and which can be the dominant source of error for very long integrations, particularly in the planetary case. And the final item is homework. The wiki contains a set of 4 or 5 problems ranging from analytic problems to conceptual ones to to one problem involving using the Mercury software to do a long planetary integration. The homework session devoted to this is tomorrow afternoon, and I'll be available in the astrophysics library at that point and throughout the school if you have any questions or there's anything I can help with. Okay, are there questions at this point? Basically, the best way to think about this is to imagine that the geometric integrators are integrating a Hamiltonian, which is, they're integrating a Hamiltonian exactly, but it's not the right Hamiltonian. That is, they're integrating some numerical Hamiltonian, which is close to, but not the same as the real Hamiltonian. The main source of those oscillatory errors is simply that because it's integrating slightly the wrong Hamiltonian, in a certain sense it has slightly the wrong initial conditions. There are techniques that allow you to reduce those energy oscillation errors simply by displacing the particle a carefully chosen amount when you start off. That sort of puts it on what's closer to the correct initial conditions for the integration that you're trying to do. One way of seeing that is, in fact, if you think about Leapfrog, I've been telling you that Leapfrog is much better than modified Euler, but in fact, after the first half step, Leapfrog is modified Euler because it's just a sequence of kick and drift steps. And one way to think of Leapfrog is that the first and the last half step in Leapfrog are transforming to and from a slightly different set of initial conditions that are allow you to minimize the errors with modified Euler. So most of the error is the wrong initial conditions. If you talk to people who are enthusiasts about geometric integration algorithms, they'll say you're asking the wrong question. What they'll say is, who cares what the energy error is? The important thing for a qualitative understanding of the physical system is to have a solution that has the right geometry and phase space. And if it has the right geometry and phase space, who cares what the energy errors are? So the real enthusiasts for geometric integration will say all these questions about how big the energy error is and whether it's first order or second order or fourth order are missing the point. Well, that's actually one of the homework problems. But the basic answer is the angular momentum isn't a good thing to look at because Leapfrog and modified Euler conserve it exactly. So it's no help. On the other hand, it means that that is another geometric property they have that's very nice. They conserve angular momentum. Okay, we're actually early. I'm not sure if coffee is available, but if so, go for it. Thank you.